From the previous video, hopefully you recognize the trick here is to concentrate on the center of mass. Okay, so each individual particle is bouncing around and being chaotic, give you a headache. But if you add everything together and just keep track of the center of mass of the entire system, this is going to make life easy. So let's just go through and talk about the center of mass a little bit and what it's doing. So not just the position of it, the velocity of the center of mass, the forces, that it feels like all the forces are concentrated at the center of mass. So everything that you learned in statics about the center of mass, we're going to do kind of the next step of that for dynamics. And it doesn't matter if those particles are connected to one another in a single rigid body or if they're independently moving. If you draw your system boundary around some group and just keep track of the entire group, add everything together into an equivalent system where everything is acting on the center of mass, that's what these problems are going to be about. Here's just a review of what the center of mass is, and it is a moment calculation. What we're doing is taking some system, and again, this can be one single solid object, or it can be a bunch of particles, and we're just drawing our system boundary to include all of those particles in it. And to figure out the position of the center of mass, this is an R cross F thing. It's a moment calculation. And you can decide where to take the moment around any spot you want, and it'll end up calculating the same center of mass, but it's an equivalent system. So you add together each individual piece of it. So R cross F, just each little chunk of mass. And this is going to be equal to everything added together and just what the center of the thing is doing. And the center has a location, and that location is the center of mass. Okay, so you have all of the individual pieces added together, and they add together to what kind of, it's the microscopic view and the macroscopic view. So the center of mass and what that is doing, that's sort of the average of the system and the big macroscopic view. And the big view, the big picture here, is a lot more friendly than the microscopic picture. So here we go. The center of mass has XYZ coordinates. You get to those XYZ coordinates by just looking at the XYZ positions of each individual particle. So if you have the XYZ coordinates of each little piece here, all of the XMs added together divided by the total mass, that's where the X coordinate is. Likewise for Y and for Z. So again, you're just adding together each of these individual parts, and this is, if you don't remember finding the center of mass from statics, get those notes back out again and review it, and I'll post a statics video too, going through this as well. What happens if we take the time derivative of this? So we're not just interested in the static position of the center of mass, we want to know how the center of mass is moving around. Okay, so all this is going to do is change positions into velocities. Okay, so now you have the same idea, only we're looking at the velocity of the center of mass now. And to figure out kind of the average of what the entire system is doing, you're going to add together the individual MVs of each piece. And again, this is going to happen in the X, Y, and Z direction. So just like you split forces into X, Y, Z direction, or positions have an X, Y, Z, velocities you split into X, Y, Z positions too. And the X component, you're just adding up all of the X components for it. Y, the same thing. Okay, so you have individual particles. Each individual particle has a mass and a velocity, and you can split that velocity into its X, Y, Z components. And if you add all of those individual particles together and just get the global big picture of it, that's what the center of mass velocity is doing. Okay, MV. Do you remember what MV is? This is the linear momentum of your system. So let's go ahead and talk about linear momentum again. It has the symbol of L. I don't know, I guess L for linear. So linear momentum, MV. And this is sort of an object in motion wants to stay in motion, object at rest wants to stay in rest. That MV is going to be cruising and not changing until you have an external force acting on it, okay? So remember this stuff, the same things that applied to an individual particle are now going to apply to a group of particles. So for an individual particle, a single space guy, he has some initial MV, right? And that MV is going to be changed by a force acting on it through a time. This is an impulse. And then you end up with another MV at some time later. So you're coming in with some initial velocity, a force acts on it, and that force changes your velocity to some new thing. And you can define your system as just a single particle, or we can put summation signs on this. We can draw a larger boundary and our system can include more than just one particle, in which case you just have to be very careful to keep track of what your system is, what is crossing that system boundary to change the entire system, and at the very end you're still keeping track of that entire system of particles. Okay, so this is, you have particle 1, particle 2, particle 3, some n number of particles, and they all have some initial velocity, and there might be some kind of a force that would change the overall global picture. And to get the overall force acting on the system, you're going to have to add up the forces acting on each particle. Now, a little thing to say about the forces acting on each particle. These are going to be external forces. If it's spaceman bumping against spaceman, that would be equal and opposite. So he pushes on him and he pushes on him, and after you sum all of those together, anything inside of the system is equal and opposite and cancels out. So the only forces you have to worry about here that change the center of mass motion, the only forces you have to worry about here are external forces that are crossing the system boundary. So this is like if wind is blowing against it, or if there's a wall that everybody is bouncing up against, or a magnetic force, or gravity is acting on the entire system. So there has to be some kind of a global force that is not, you know, equal and opposite, that's going to be canceling out over here. So you have adding up everything that's going on for the whole system, the forces acting on the whole system, and then coming out of here, it might have a new velocity. Now, if there are no external forces happening, that's when you can say, well, all of these initial MVs bouncing around, and maybe there's collisions happening between time 1 and time 2. So the individual velocities of the particles might be changing between 1 and 2 just based on, you know, the collisions between particles. But collisions between particles will not change what the center of mass is doing. Okay, so if there's no external forces, the overall center of mass is not going to be changed, even though individual particles might be bouncing around and doing something a little bit different. But those internal forces don't change the big global, the big picture piece of it. Okay, so you have all the little pieces, and if you add those together, you have the total mass of the system, m1 plus m2 plus m3, m plus the entire mass. The velocity of the center, that's that little line over the top, as we're talking about what the center of mass is doing. So you have the global position of the entire system, and then you look to see if there's any external forces happening on that. And if there's external forces happening on it, then the center of masses, that velocity is going to change at the end of it. But if there's no external forces happening on it, then the global picture, what the center of mass is doing, will not have changed, and you'll have conservation of linear momentum. Okay, so we've got linear momentum. We're adding this stuff together. What if we put an R in front of everything? Okay, angular momentum. And it's the same thing. If you can do moments in statics, R cross MA, R cross F, you can do R cross MV. It's the same thing. You know how to do a cross product. You know how to split velocities into IJK components. Where is your position vector pointing from? Well, you can take the moment around any point you want. You can take the angular momentum around any point you want. So just pick a point, and if there's no forces that are changing the rotational motion of that system, then you have conservation of angular momentum, just like you would have conservation of linear momentum. So anything that we did before, you can stick an R in front of both sides of the equation and see how your angular momentum is changing as well. So angular momentum, for some reason, has the symbol H. I don't know why it's H. That's the most horrible thing about this book, is just trying to remember what symbols go with what concepts. So if you see an H, R cross MV. And again, what we're going to do is, instead of just keeping track of one particle, you're going to start, there's a big summation sign here. Okay, so what's R cross MV of the first one? What's R cross MV of the second one? R cross MV of the third one? You just keep adding it together and adding it together, and that is going to add to what the overall big picture is doing. So the rotational tendencies of the system as a whole. If we can talk about velocities, we can also talk about accelerations. So if you want to know what's the acceleration of the center of mass, well, it's a combination of what all of the little guys are doing. And again, internal forces, MA, we're talking about forces here, internal forces cancel out, and the overall acceleration of the center of mass, that's only going to change if external forces are applied to your system. So if there's no external forces applied to the system, then this little guy, the only acceleration that's happening here actually is going to be from external forces, because everything else is going to cancel out. So yeah, internal collisions between particles don't change anything. And it's, you know, the microscopic picture is changing all the time, right? Each of these particles is undergoing collisions, and their velocities are changing, and their acceleration is changing. And so the microscopic picture is a mess. It's a chaotic, crazy mess, and you don't want to have to do all those calculations to figure it out. But if you add it all together, the overall picture, the center of mass is going to be just headed out with a constant velocity, constant acceleration. That position is not going to be doing anything weird. So if you zoom out and blur your eyes so you can't see the chaos going on at the microscopic level, you just see the big picture. The big picture looks like what we did in chapters 11 and 12. It looks like a point mass. It looks like, you know, x equals x naught plus vt. It looks like just the normal kinds of problems that you've done. So zoom out and get a big picture view for these problems, because that's what's going to save you. Okay, so it's a force, internal forces versus external forces. So internal forces, what we're talking about is particle-to-particle collisions. Those occur in equal and opposite pairs, and when you add them all together, that summation sign, you're not worried about internal forces anymore. So we're only worried about the wind blowing on everything, a big wall that's in front of everything, some kind of an external force that wasn't a piece of your system boundary. So draw your boundary. So if my system consists of the particles and the wall is not part of my system, anything that's not part of my system, that's external. And external stuff changes how my system. So you have to, you know, what is inside of your system and what is not inside of your system, and how are those two pieces interacting with one another. One other thing that they're going to talk about is equivalent versus equipolant. Equivalent means every single particle velocity is the same and every little piece of it is the same. Equipolant means we're not worried about the details, every little exact detail being the same. We're just worried about the overall picture being the same. And that's another thing. So if you hear the word equipolant, that's another big picture word that we're not worried about the individual little bouncing around motions of things. We're just looking at the big picture, and the overall big picture is equipolant. It's not exactly equivalent, but it's close enough, okay? So here we go. Here's the moment. If you can do angular momentum, you can do the moment, R cross MA, and it's the same thing you did in static. So you pick a position to take the moment around, and it's from the axis of rotation to each particle, and you're worried about the forces acting on each particle, and you're adding all of these R cross F, R cross F, R cross F. So the position vector is from your axis of rotation to where the force is applied. You split everything up into IJK components, you take the cross product. So you can do moments, you can do angular momentums, you can do linear momentums, everything you did in statics, and you really have to tie it back to what you know. So just take what you know, and you're building on that and expanding that to now you're summing up more stuff. So you're just keeping track of a larger system happening. Here's just a review. So position of the thing, and you can call that position a radius, some radial position from an origin. You can break your position into XYZ components. Okay, position concepts, those go to velocity concepts. If you just put dt on both sides of this, they go to acceleration concepts. For the current chapter, we have discrete elements, so individual independently moving particles. In the next chapter, it's going to be solid chunks, rigid bodies, but it's the same concepts either way. You're just finding where the center is, keeping track of the center, and life will be easier if you just look at what that center is doing. Here's an example. So what we have is a 30-gram bullet fired with a horizontal velocity of 450 meters per second, and zoop, it becomes embedded in block B. We're talking a plastic collision. They're stuck together, embedded. And block B has a mass of 3 kilograms, quite a bit larger. So little teeny 30-gram bullet, 3 kilogram block. After the impact, block B slides on the 30 kilogram carrier. So this is the big mass here, 30 kilogram carrier. So zoom, hits the block and the bullet, zoom, hit the carrier. Impacts the end of the carrier. Knowing the impact between B and C is perfectly plastic. Okay, elastic impacts versus plastic impacts. For plastic, it's a raw egg smacking into the ground. They're stuck together. It's not bouncing back. Okay, it is not recovering itself. There's no coefficient of restitution is 0 for plastic impact. It doesn't bounce back. So plastic impact, they're all splatted together. They're not bouncing away from one another. We have a coefficient of kinetic friction between B and C. Okay, what can you think about the friction force? Is the friction force internal or is it external? Well, how are you defining your system? If you're defining your system as just the block, friction is external to the block. But if you've defined your system as the bullet and the block and the cart all together, there's equal and opposite friction forces between the cart and the block, okay? So it all comes down to where you draw your system boundaries of what you have to worry about as being external versus what's just going to cancel out and not have any influence at all on what's happening. Okay, so we've got some friction, and we want to know velocity after the bullet comes into the first impact and the final velocity of the character. Okay, so zoom, what's the velocity after the first impact? For that system, maybe we have just the bullet and the block, but we're looking at just right before and right after that, so it's not really sliding it around yet. And then the next impact, the bullet and the block combination slam into the carrier, okay? And in that case, your system is going to be everything. And again, we're not going to worry about the friction force because it's internal to the system. Write out what you're given. Write out what you're going to find. Keep yourself organized for this stuff. So we're given masses, initial velocity. We have a plastic collision, which means our coefficient of restitution is 0. We're given a friction coefficient, but I don't know that we really need that because we can set it up so that that piece of it is internal. And we want velocity after the first collision and velocity of everything together after the second collision. So 2 equations, 2 unknowns. What 2 equations are we going to be using for this? A good way to organize these problems is to set it up with a table. So we have jump, first collision, jump, second collision. Initial state, state 1, we have the bullet moving and nothing else moving. So there's the velocity of the bullet, and the block and crate have 0 velocities. Initial state. So first collision goes from state 1 to state 2, right? We have M1V1 plus force TT goes to M2V2. Okay, this is state 2. This is M2V2. And the second state is they're stuck together. They're stuck together means they're both going at the same velocity. After that collision, the bullet and the block both have the same velocity. They're stuck together. So here's another unknown. And then we have from 2 to 3. Okay, so the block is going to slide to the end, slam into the end of the carrier, and it's a plastic collision again. Their velocities are all equal to one another again. Okay, so VA equals VB equals VC. We have 3 states, and we have linear momentum between 1 and 2, and linear momentum between 2 and 3. So here we go. Let's start writing some equations out here. And as you write these equations, so all of the MVs initially, F dt, and F dt for us is 0, okay? We're doing an instantaneous. Our time 1 and time 2 are like right next to each other, okay? It's very quick, and so we're not going to worry about any teeny itsy little friction force. The friction force is so small compared to, bam, that impact of the bullet that we don't need to worry about any external forces. Okay, so such a small time step and such small magnitude of friction force compared to the impact force and the impact force, the bullet on the block and the block on the bullet, that's equal and opposite. So when you add up the bullet on the block and the block on the bullet, one's positive, one's negative, it adds to 0. You don't have to worry about the internal forces. Okay, so initial velocity, just the bullet. Final MV is the bullet and the block moving together. And so that final velocity coming out of there, it's just a mass ratio, right? So it's just a little teeny bullet divided by the bullet and the block together, and that's going to be the velocity ratio. So a huge velocity of the bullet, 450 meters per second, and that block slows it down to 4.45 meters per second. And this difference in velocities, well, that's the difference in weights, okay? So that great big weight is going to totally slow it down. And like free body diagrams and kinetic diagram, take each piece of this equation and draw a picture of what's happening. So state 1, what is the initial conditions? What's our initial state? What's our initial MV1s? If you're going to talk about F dt, any kind of force, draw a free body diagram of that sucker, okay, to keep track of all the forces. And then our final state, draw a picture of it. What's happening in this second state? Draw a picture of it and just figure out one little piece of this equation at a time. So ignore everything except for MV1. Just figure out what is all of this stuff going on. What is all the impulse going on? And walk through one piece at a time and then put the whole puzzle together. Okay, so that was 1 to 2. Now let's do 2 to 3. So initially we have the bullet and block going together. F dt, our impulse, but these are our system boundary is now the cart, the block, and the bullet all together. And these friction forces are equal and opposite. And when you add those equal and opposite together, it is 0. Impulse is 0. The final system, plastic collision, everything is stuck together, traveling at the same velocity. Okay, so we have initial velocity of these two guys acting together, 0 external forces. We're going to say there's no friction. Like if the wheels were rusty and there was some external force, or there was friction slowing it down somehow, or it was going up a hill and gravity was, but we don't have any of that. So it's 0, and the final situation of everything stuck together. So once again, it's going to be just a ratio of the masses. Now, something interesting here, we didn't have to go from 2 to 3. We could have gone 1 to 3. Okay, we could have, instead of gone from the block and the bullet and the intermediate velocity, this was equal to what was originally coming into it. Okay, so for this equation, it doesn't matter what you call your starting position and what you call your ending position. So you can start wherever you want. You can end wherever you want. This is kind of a nice thing. You can grab any little snapshot in time you want for the start and the end. And this final velocity, you can get there by going through this intermediate step and the intermediate mass ratio, or you could have just jumped from the initial state right to the end. Okay, so you could have said initial bullet goes into it, and final system is all of the masses stuck together. So here's the initial bullet and velocity and all of the masses stuck together, and you could get the exact same thing if you plugged in that intermediate velocity too. So that's another kind of little trick, is you don't have to step through every little piece of it, and you don't have to solve for every little velocity going through the process. You can jump from one time step to any other time step you want in here. Okay, so here's the final velocity, 0.41 meters per second. And we are traveling to the left here. That's the direction the bullet was originally traveling, so that maybe call that negative, I guess. Here's another scenario. Okay, same thing, same bullet, same block, same cart, same weight, everything the same, except let's say that instead of the bullet becoming embedded in it, the bullet is going to travel through the block. Okay, so we're no longer having a plastic impact. The bullet is going to go through the block and hit the carrier. So right through the thing. And then the block is going to slide to rest to hit the carrier. So we have a different kind of impact happening with block. Instead of becoming embedded in the block, the bullet is going to go through the block, through the 3 kilogram block. If we write out the table of timeline of events for this, we start with the bullet velocity. Okay, after the first impact, the velocity of the bullet and the velocity of the block, these are not the same because they're not stuck together. So we have a new complication here. We have a new unknown. So the bullet has some velocity and the block has some velocity, but they're not stuck together because the bullet is passing through the block. The next situation is the block is embedded in the carrier. So the bullet and the carrier, these two have the same velocity. They're stuck together, and the block is still moving with what it was moving with, right? The bullet, it's going faster. So this is going to happen before the block reaches its final velocity. And then the last state is going to be the same as we had before. The last state, everything is stuck together. Now, ask yourself the question, is how we get to this last state, is that going to change this final velocity? So we're starting, same masses, same initial velocity. We're ending, same idea, everything's smushed together. is what's happening in these intermediate steps going to change from 1 to 4 at all? Are we going to have a different ending velocity coming out of this? We're not. Hopefully you can see what that is. So we can jump from 1 to 4, and if you jump from 1 to 4, it's the same process. Now a little bit different things happening in between here, but we should get the same thing between 1 and 4 as we had before. So let's walk through the equations. Now, how many unknowns do we have? We don't know VA, we don't know VB, we don't know VAC, we don't know. We have 4 unknowns. 4 unknowns, we need 4 equations. How many impacts do we have? So from 1 to 2, there's a linear momentum equation we can do from 1 to 2. From 2 to 3, from 3 to 4, that's only 3 collisions that we can write mv plus fdt equals mv equations for. So if we only have 1, 2, 3 equations, how are we going to solve for 4 unknowns? We're going to have to reach into our bag of tricks and pull out some other equations. And all of the equations that you have learned, kinematics, kinetics, energy balance, linear momentum balance, angular momentum, any of those can be applied to any problem you want, okay? So you've got a big bag of equations and just keep pulling them out until you have enough to solve for what you need. So here's the process. So the bullet is now going through the block. See, the bullet is now with the carrier and the block is back here, and then the block's going to catch up with it. So that's what's happening for this scenario. So here we go. From 1 to 2, the bullet goes to bullet and the block moving. So we have 2 velocities here, 2 different velocities happening for this first impact. We still don't have external forces, so we don't have to worry about FDT. It is MV goes to MV. From 2 to 3, the bullet slams into the carrier. So the velocity coming off of that first impact is now going into the second impact. And here's another unknown, is the velocity of the carrier after the bullet gets stuck in it. Okay, 3 to 4. So coming out of here, the velocity with the carrier, and for B, for our block, okay, that's what's coming out of here. That's the velocity. See how this table, make one of these tables, because you'll get real confused. This is a good way to organize it, and you have to get this stuff organized. Okay, so here's the block, and the final situation is everything is stuck together going at some final velocity. 3 equations, 4 unknowns. My favorite equation to use is an energy balance, because energy is not a vector. You don't have to worry about what direction it's going in. It's just, I don't know, energy balance is my favorite equation to use. So let's throw that in there. Now they give us a coefficient of kinetic friction. And we're given block B slides 0.3 meters. We're given a force, friction force through a distance, F dx. F dx, that's another reason to use an energy balance. So remember where that energy balance equation came from? F equals ma equals m dv dt equals m dv ds ds dt equals mv dv ds. Okay, so picture in your mind, mv dv ds, or force ds equals mv dv, or force ds equals 1/2 mv squared. Remember that little derivation? So we have kinetic energy, and that kinetic energy is going to be changed by some kind of an FDS. FDS can be potential energy, it can be mgh, it could be 1/2 kx squared, or FDS could be friction, slowing it down. But whenever you have force and distance, energy balance should immediately come to mind if you hear force and distance in the same problem statement. So, and this is strange. We have linear momentum is conserved, energy is not conserved. That's always a confusing thing, because 1/2 mv squared, mv, and it seems like if linear momentum is conserved, wouldn't that mean energy is conserved too? Well, no. the friction is heating stuff up. It's sucking energy away from the system. So don't confuse conservation of linear momentum with conservation of energy. Those are two very different things. Even though they both have M's and V's in it, they're different monsters. Okay, so here's our 4 equations. Linear momentum, linear momentum, linear momentum. And these 3 are from 1 to 2, 2 to 3, 3 to 4. Okay, so these are the 3 collisions. And then the 4th equation we're going to throw in there is our energy balance. So remember these funny T. T is our 1/2 mv squared. And U, ugh, work, force through a distance. So we have NU, this is our friction force. It's just the weight of the block. And then we have final energy coming out of it. So all the masses smushed together with the velocity, and you're going to have to figure out what velocities are going into this, okay? So for the energy balance equation, instead of just having the kinetic energy of one little particle, you have to add together everything that's happening in your system. So you have the kinetic energy of the bullet and the carrier together, the kinetic energy of the block. So decide what your starting system is going to be. And this would be the good starting system because that's kind of where that friction force is acting. But just grab an instant in time, and the force that's going to suck energy away from it, if it's conservative or non-conservative or potential energies, any kind of FDS you're going to have to add into here. And then you have your final energy. Maybe we should plug this through. Would it matter if we went from just the bullet moving and jumped all the way over to everything moving together? It would still be the same U. So try and calculate that a couple of different ways to go from 1 to 4 or 3 to 4. The important part is to draw your system boundaries, decide what all you're going to be keeping track of, and then instead of just adding the kinetic energy of one little piece, you have to, anything that's moving, you have to keep adding that up. There's a big summation sign. It's just, yeah, the only difference between this and what we have been doing is big summation sign. So here we go. Crank through 4 equations, 4 unknowns, plug in all of our masses and velocities, and so there's different intermediate velocities going on, right? So we're going from, what was it, 450 meters per second, and then it zooms through the block to 306, and then it hits the carrier at 1.4, and then the block hits the carrier. But the final state, it's still 0.41. It's the same thing. So for whether that bullet goes right through the block or it becomes embedded in the block, because state 1 and state 4 are the same and everything in between is internal, it doesn't matter how we get from 1 to 4. The final velocity is the same. And this goes back to like an equivalent versus an equipolant system. And sometimes these center details of what's happening, we're not going to care about those center details. We're just going to skip right to the end. Okay, so there's that example. Here's another example, and this one is going to be a really good one for thinking about implications of the center of mass of the system. So let's go ahead and read through the problem statement. Car A weighs 4,000 pounds, car B weighs 3,700 pounds. They start at rest on a 22-ton flat car, which is also at rest. Okay, so are you taking all this in? So we're starting from rest. Everything is at rest. Car A and B then accelerate and quickly reach constant speeds relative to the flat car of 7 feet per second and 3.5 feet per second respectively. Then they decelerate to a stop at the opposite end of the flat car. Okay, so start from rest, and then they both drive, they speed up and slow down as they reach the other end of the flat car. We're going to neglect friction and rolling resistance. This means we're not going to have any external forces. Determine the velocity of the flat car when the cars are moving at constant speeds. Okay, I don't know if you've ever stood on a skateboard before and without putting your foot on the ground. Okay, so if you just kind of lean back and forth, what would happen? Can you get yourself to move if you never put your foot off of the skateboard and onto the ground and never push off the ground? If you don't push off the ground, if there's no external force, okay, and there's no external force in the system, would you be able to get that skateboard to move around anywhere just by scooching your weight back and forth on it? Okay, and this is the center of mass. Where is the center of mass going to remain for this system? Okay, so here's our given. We have the initial masses of the two cars and the train. We have the initial velocity starts from rest. We then have the cars relative to the train, so that's that A/F. That's car A relative to the flat car B relative to the flat car. And remember all of this stuff about how the velocities add together. So the velocity of A is equal to the relative velocity plus the velocity of the flat car. You can kind of add those vectors together. So there's their relative velocity, and we want to find the velocity of the flat car after these guys speed up to their max velocity and then before they slow down. So how would we do that? Let's just draw some pictures about position A, position B, position C. Okay, so they start on the right, the cars are driving to the left, and then at the end, they're over here at the end of the flat car. Okay? If we drew the center of mass for this system, would the center of mass change? Now remember, there's no external forces in the system. So if there's no external forces and the initial velocity of the center of mass is 0, and there's no external forces to change that 0 velocity, the center of mass of the system is going to stay put. It's going to have a 0 velocity through the entire process. So even though the cars are moving around and the train is moving around, the center of mass is not moving around. It starts with a 0 velocity, it ends with a 0 velocity. There are no external forces changing the overall center of mass. So this guy, the center of mass, is going to stay constant through the whole thing. So the cars go to the left, the train goes to the right, and between the two of them, they will balance it out so the center of mass stays put. And that's, if you've ever played around on a skateboard, you'd experience the same thing where you're not going to be able to move anywhere unless you apply an external force. Your foot has to go and hit the ground, get that external force before the center of mass can move anywhere. You have to apply some kind of an external force. Okay, so let's work through our linear momentum balances. And again, these tables are very convenient for working this through. So initial state, 0 velocities. Final state, 0 velocities. But in between, we have the cars are moving and the flat car is moving. And we want to figure out what the flat car is doing. And remember, all of this is going to have to add up so that the center of mass keeps that 0 velocity. So from 1 to 2, we have all of those 0 velocities are going to have to add together to what the two cars and the flat car are doing. So if the velocity of one is positive, the velocity of the others will be negative, and vice versa. Okay, and then that 0 velocity will go to the final state as well, so it's kind of symmetrical on both sides of that. Here we're given the velocities of the car, we have the masses of the car. Now these are the relative velocities. That's not the absolute velocity, so you have to remember how to add relative velocities together to get the overall velocity and substitute in these vector additions. Okay, so the relative velocity, that's the difference between the two. And we're going to substitute that in up here into our momentum. So over here for the flat car, we can put in the relative velocities. And once you substitute this in, you can see that the cars are going to the left. That means the flat car has to move to the right. Study that, see if it makes sense, and then kind of think through implications of that center of mass and how that center of mass sitting there at 0 through the whole process, that's what really allows us to link everything together and balance everything and figure out what the whole system is doing.